today we're going to do more linked lists, and we're going to look at inserting more and deletion if we get time for deletion. Just a few announcements before we start. So today we've got the assignment 2 live stream. Hands up who's looked at the assignment or started the assignment already. Okay, cool. Now there's some parts of the assignment right now that if you don't know linked lists, that's going to be a bit hard for you to do. But there's some parts of the first stages where that's going to be okay. So you can get started now. Yeah, so we've got the live stream at 4:30. So you can come to the YouTube link. There's a link from the assignment spec as well. And there'll also be a recording available. But if you turn up to the live stream, then you can ask questions in the live chat. So that's the benefit of that. The due date is Friday, week 10, 5 p.m. Don't leave it to the last minute, of course. I've said that a million times. The other thing I wanted to talk about was, we've seen a pattern of many students using a lot of ChatGPT. So I just want to warn you, just be very careful in your assignment too, because if one person uses ChatGPT to generate some code for a function, you can imagine out of 1,000 other students who might have used ChatGPT to generate those functions, you might end up with the same code, which will get flagged for plagiarism, even if we can't look at it and see that's obviously from ChatGPT. So there's a few ways you can get caught out. But I guess the biggest problem is, you're not gonna have ChatGPT in the final exam. So it's better that you don't over rely on it. Okay, so that's just a little bit of a warning. And that goes for labs too, by the way. You need to be able to, the exam's coming up in a few weeks, so you've got to get used to debugging and coding without over reliance on things you can't use in the exam. Okay, and if you are a bit behind or you need more help and that's why you're doing it, or even if you're not doing it and you want to go to revision sessions, there are some on this week. Wednesday 12 to 2, Friday 2 to 4. You can sign up. You can vote for your topics. I think the votes are still open. So don't forget to make use of all the help. We've always got help sessions too. Okay, so today, last lecture you might recall we did some linked lists. We did some basics, explained what they were, printed a list, and we inserted nodes at the beginning of the list. So today we're going to look at, we'll do a bit of a recap. We'll look at inserting at the tail or just anywhere within the list. And if we get time, we'll do some linked list deletion. All right, anything we don't finish today, we'll finish on Thursday. As usual, we've got a link to the week 8 live lecture code. But to start with, I want to do a Kahoot just to see how everyone's going with malloc and linked lists because it's really important you understand the basics before we go on and do something more difficult. So everyone, let's do a quick Kahoot. That will hopefully get our brains going too. Oops, that's not what I'm looking for. So I think this is malloc and very basics of linked lists. Oh. No players so far. Okay, here they come. Oh, yeah. Is it? Oh. That's not very loud. All right, is there anyone still trying to join in the room or at home? I'll give her another minute to wake up and a little bit and join. Okay, let's go. I'll start now. Actually, look, some of the other answers are technically right, you know. The heap is still RAM and memory, but most specifically, it's on the heap. It's definitely not on the stack. The stack's where our local variables are stored, and that's all managed automatically. Heap is the memory we get when we do malloc. Okay. So you might feel ripped off if you said memory or RAM. Okay. Okay, so yeah, memory can be allocated dynamically at runtime as needed. So while your code is running, you can malloc more and more memory as you need it. You don't have to know in advance how much memory you're going to need. And the memory you allocate on the heap persists after your function call has returned. So if I've got local variables in a function, what happens when the function finishes? They live on the stack, they get popped off the stack. They're not there anymore. They don't exist. That memory gets used for something else. So heap allows us to have memory that still exists, still holds all of our variables once our function finishes. Yeah, the lower address, I just threw that in to confuse people. And the heap doesn't automate the allocation and deallocation of memory. That's what the stack does. All right. Okay, lively bison. Okay, very good. Most people have that. Yeah, don't forget, yeah, you need the size of the thing multiplied by how many things you want. And what are the, yeah. All right. The rest just all have one slight sort of mistake. All right, someone said on the last slide, wasn't it 10? Did I have the number 10 instead of 5? I'll go back and check. All right, yeah, free wasn't called. Okay, we didn't call free. Probably if you ran your program, if you compiled it and ran it, you'd think it worked fine, and it probably would. But if we ran it with DCC minus leak check, it'd tell us we've got a memory leak. So in this course, we want you to do a free for every malloc, and in assignment 2, we will check that. Right. Okay, cool. Yep, that's correct. You have to manually free the memory. Yeah, sometimes people think the memory is lost forever. That's not true. It's just while your program's running, you're wasting memory. And if you keep doing that, you might run out. It'll all get restored and be useful on your actual computer once your program finishes. Okay. This is cruel, really. They all look so similar. I hope one of them's right. Wow, most people got it. And it's also cruel because the colours get shuffled around so that it was hard to see which one you're going to pick. But let's have a look. All right, this one here is missing the star. So this has to be a pointer to another node. Okay, for it to be a linked list. And actually, yeah, A is problematic, but we won't talk about it too much. Yeah, B was the right one. Why is C wrong? Yeah, it has to be a pointer to another thing of the same type. So a pointer to another struct node. Down here, that's just pretty wrong. Okay. Oh, free typing this time. I don't know. Okay, fair enough. Yep, so if you want to know the size of your struct node, this means size in bytes. Don't calculate it yourself. Use the size of function and say size of struct node. All right? Okay. Okay, yep, this is good, and a lot of people got it, so that's great. Blue, remember we need that star. New node has to be a pointer. Okay, last question coming up. How much time did I give for this question? Oh, 30? Okay. No, the counter that I was looking at here was on a different spot. I was getting confused. It's all right. Okay, yep, this is an empty linked list. Struct node star head is null. There's no data in the list, so the address that it's pointing to, there's no address to point to the first piece of data. Okay, all right. Let's see who won. And yeah, if you're in the room and you came first, second, third, fourth or fifth, put your hand up. Well done. Do we have Wonderhawk, Amusing Bobcat, or Charming Bear? Ah, awesome. Anyone else? Okay. All the people who came fourth and fifth who I missed. If you're in here, put your hand up as well. Okay. Let's get that music off. Okay, I think people did really well on that, considering you've only had sort of one lecture on it. And I didn't do a recap first. So I'm just going to quickly do a bit more of a recap on linked lists. So please pay attention, because if you don't understand these basics, it's going to be impossible to understand how to delete something from a list or insert something at the tail of a list. So remember, these are the important types that we'll be working with, right? We've got a linked list. Our linked list variable is just a pointer to some kind of node. And the node that we've got and that we'll be using for a little bit is, we're just going to work with a struct like this for a while, has one int and then a pointer to the next struct. Later on, or if you've already looked at the assignment, you'll see you can have any type of data in here. It doesn't have to be one int, but for now, we just want to keep it simple to learn the linked list mechanics, which isn't simple itself. So it's a bit like a scavenger hunt. We've only got a variable that keeps track of this first chunk of data. So it'll know the address of the first node. And the first node has a value in it, but the first node also has the address of the next node in that next field. Shh. Sorry. And yeah, this next node has the value 17, but it has the address of the data in the next node, right? And the next node has the address of the data in the next node. When we get to this node here, we've got 5 as the data and we've got null as the next node. That's saying we're at the end of the list. There is no next node, okay? That's how we can tell when we've reached the end. If we've got an address in this node that's not null, we know that there's another node after it in the list. Okay, are there any questions about how that kind of works? Yep.
How does the linked list know the address when you haven't given it the address?
Well, that's the thing. When we start off, we've got no information and we've got an empty linked list. and we've got null in it. There's no data, it doesn't know any addresses, but then every time we do a malloc to create all of these nodes, and when we do a malloc, that gives us back the address.
Oh, so the malloc automatically gives it, so you don't have
So the malloc gives us the address, then we have that address, and that's how we can connect it all up. Yep. Okay, so let's have a look. And this is how we typically visualize our lists, right? I've got some kind of variable that stores the address at the beginning of the list or the first node in the list. We often call it head. It could be first, it could be list. It's just a variable name. So we're saying this struct is at address 28. Then this struct has the value 13 and it's saying the next struct is at address 80, etc. Okay, so imagine that these at the top, these are just fake addresses I've made up. But each node connects to the next node. All right, and because of that, we can't do what we do with arrays, like say, I want to go straight to index 99. We would have to start at the beginning and have a loop and go through and count our way up and work out when we looked through 99 nodes. Okay. So here, let's just revise building some sort of linked list. We're starting with an empty linked list. There's no address of any node because there are no nodes yet. So the head is equal to null. Then this is where we can do a malloc. And we wrote a nice function that can do this for us, but this is kind of the raw code. We can do a malloc to create a chunk of memory to store a node in. Then we can set the data inside it, because remember, when we've got a pointer to a struct, we use an arrow. So I can go and set the data field to 21. Now, because this is just one node and there's no other nodes to connect it to, we're setting the next node. So we're setting this data field in the node to be null. Now at this point, this is a linked list of size 1. All right, we've got the address of some node, there's data in it, it says the next one's null, so there's just one node in this list. Does anyone have questions about this? Okay. Then what if we want more nodes? Well, we do another malloc. And when we do the malloc, it asks for the chunk of memory and we get some address back. Now, in this case, we've stored the address of this new node in a variable called new node. Right, and then we can take that address and go to it and set the data inside, and I've done that to 99. But what do I want to set this next field to be? So in this example, we're adding this node to the start of the list. So I want new node to actually end up being the first node. I want the node after it to be this node I've already got in the list. Okay, so I'm trying to connect this new node to what's already in the list, but have the new node at the start. What's the address of this node that's already in the list? Well, in this case, it's 0x88. Actually, I'll get my pen. Why am I drawing with my mouse? That's what we want in there. But what's the variable that has this value in it? Head, yeah. So we're saying new node next equals head. So what it's actually doing is copying that address into here. That's what it's actually doing. But we can think of it as the new node is now pointing to whatever's already in that list. It's pointing to the beginning of that list. And if there are lots of other nodes in there, they'd still be in there too. We're just adding this one to the beginning. Okay, any questions about that? Oh, and we can see it on the next slide where I've actually done it, I think. Oh, but right now, what have I forgotten to do? Yeah, I've forgotten to update head. So head is not pointing to the beginning of the list now, which would be bad because now if we wanted to print out our list and we started printing from head, we're not including that first element. We need to update the beginning of our list. So anytime we're taking something off the list at the beginning, adding something to the list at the beginning, we need to make sure our head variable's updated and it knows that that new node exists and is connected to the list now. So to do that, that's quite easy. we just say head equals new node. So what that's doing in the code is it's copying this address into this head variable, but you just think of it, well, now that new node is the head of the list. The head of the list is now that new node. Yep.
Are these nodes two separate things, or is the second node related to the first node?
They're not related in that they're in a completely separate space of memory, and we're linking them together just by knowing the address. So yeah, it's kind of like a scavenger hunt. So when I go the head, this variable, oh, if I go back, this variable here has the address of the first node. This node's somewhere in the heap. Okay, now this node knows the address of this other node. That's somewhere completely different in the heap. So, you know, I guess it's a bit like knowing the address of a person, going to their house and they tell you the address of someone else, going to their house. Yeah. I don't know that anyone's ever really done that in real life, but that's all I could think of. Now, if we want to package that up nicely, because we'll be creating lots of nodes, we can make a function, which we did already. So basically, this function is just responsible for doing the malloc for us, so we don't have to do that again and again. Now, it's very good practice to just check that our malloc works. In most of our the stuff we're doing, which is quite small, there's probably going to be enough memory for our mallocs to always work. But actually, maybe sometimes we'll have a bug and actually be doing something silly with malloc in a loop. So it's just always best to check that malloc did work. Otherwise, we would, if it didn't work, it returns null, and we would then be trying to say null arrow data. That would crash our program. All right, so assuming we get our malloc, we're just mallocing that, and we're just setting the data field so that when you're using it, you can pass in, I want this node to have, say, 9 in it, and we go and set that in here. I want the next node to be whatever it is, and we just go and set that in there. And then we return the new node. So this is just doing what we saw before, but we've packaged it into a nice function. All right. So we did that, adding nodes to the beginning of the list. And then we looked at how we could traverse a list, which means go from the first node one by one until we're finished. What does finished mean? I guess it depends. If you were printing the list, you'd want to go right to the end. Sometimes, you know, you might be trying to search for something. Once you've found it, you might not care about continuing on. But generally speaking, it's just going through systematically one by one through the list. How do we do that? Now, we always need to make sure we've got a pointer to the head. So we've got to be careful if we're moving head around to traverse through the list, if that was our only pointer to the beginning. So typically, we make another variable. It doesn't have to be called current, but typically it's called something like current or car, which is meaningful. So we set it to the beginning, and to move it to the next one, so right now, current has the address 28. Why? Because that's the address of the first node in the list. Once we finish looking at this first node, we want to move it to the next node. So we want to move it to here. So we don't want that address in there anymore. We want the address of the next node, which we can find in here, right? This is current, this node is current. This is current arrow data. This is current arrow next. So to do this, we say, current equals head. We want to move it along. We say current equals current arrow next. Okay, if we do that again, if we say current equals current arrow next, we'll be saying current equals 60, which will have the effect of moving it along to point here. So this is a standard thing of moving a pointer from one linked list node to another. Okay. Any questions? Oh, we're still going. Now, when do we stop? If we really want to go through every node in the list, we don't want to stop until we're at null, right? We've gone through all of these. We keep going, we're at null. There's nowhere else to go. We stop. So this is how we wrote, using all of that, this is how we wrote print list. We've got a current, which we put at the head or the beginning of the list. We keep going until current is equal to, we keep going while current is equal to null. I mean, while it's not equal to null, oh my goodness. We stop when current is equal to null. For each node, we're printing out the data inside it and we're saying current equals current arrow next. So that's basically what we did here. But at each point, before we move to the next one, we're just printing it out. So you can add whatever code in here that you wanted to do for every node. Oops, and this will be sort of a general pattern, just like, oh, I've done the wrong thing here. It'll be a general pattern just like when you do a while loop or a for loop going through an array, you'll tend to do it again and again and again, this kind of pattern. All right. So any questions before we now do something different? Anything that's making you completely confused instead of just slightly confused? Yep.
For linked list, when you do like the node to another node, is every single node like a new like malloc?
Yeah, every single node is a whole struct that's been mallocked.
Okay.
And we malloc it because we don't know how many of these nodes we're going to need, and we can malloc them as we need them. And we can also then use functions and pass things through functions, create nodes in functions, and not worry about, is that function that I created it in going to end, and am I going to lose that node, etc. All right, so we've looked at inserting at the head of the list, and I did it in more detail in the last lecture. We could also have a situation where we want to insert just somewhere in the middle of the list. We'll do that later. Sometimes we want to insert right at the end of the list, which we can call the tail of the list. So that's what we're going to do now, this special case, inserting at the end of the list. So the first step to insert at the end of the list is to find the last node. Once we find the last node, then we can connect our new node that we malloc to that last node. But we can't do that until we find that last node. How do we find it? How can we find the last node, do you think? Well, yeah, so we have to have some kind of, yeah? Oh, so we had a suggestion to have a while loop while current arrow next is not equal to null. Actually, that's a really good suggestion. But, and that's exactly what we're going to do. But the main thing is we have to definitely start at the beginning and keep looking along. We have to do some kind of traversal. So when we were printing the list, our condition was to stop when we got to null. But note, if we do that, we've gone past the last element in the list. Like we've gone past it. So we don't want to do it quite like that. We actually want to stop when current is here. We want to stop one earlier. And we know that we're here because if we look at the next node in this particular node, if we look at the next address, it's null. So our condition, in this case, because we want to stop one, like right at the last node, but not when we've gone past the end of it, we do it like this. Current arrow next equals null. And then we can stop here. Is everyone sort of happy with that? Okay, if we go past it, we can't connect it up. All right, now once we've done that, imagine I want to malloc, or I want to connect a node with the value, I don't know, I think I've got it drawn on the slide. Imagine I want the value 9 connected to this. I would do a malloc, create a new node, put the 9 in it, put null because this is going to be at the end of the list. But now I've got to connect it up to this list, right? How am I going to connect this new node, called new node, to this list? Yeah, so we had current arrow next equals new node. So imagine this new node is at address, I don't know, 52. We're saying current arrow next. Remember, current arrow next is this field here. We don't want it to be null anymore. We want it to have the address of this new node in it, which means it's connected up to that. Okay? So you think of it at a higher level often. You're not writing these addresses down. You think the next one after the current one is the new one. So you say current next equals new node. All right. Oh, and I've got a nicer drawing here. This is my new node, my fake address, and the value 5. I need to connect these things up. I say current arrow next equals new node. Okay, and this field in here has been changed. So now the one after this in the list is this new node. Okay, any questions? Does that make sense? All right, let's try this in code. Unless you've got any questions. All right. Okay, inserted tail. Now, what did I just say? Okay, we've got, I'm just going to call it car. So I've got a pointer. No, I'll call it current. I'll call it current. I can type those extra few letters in. I've got current pointing to the head of my list. And I'm just going to draw a list. This is how I usually draw lists. Oh. Without all those sort of fake details. Actually, that's too big. Oh, dear. All right. That's how I often draw a linked list. Anyway, so I've got current, and right now current is equal to head. It's pointing to the head of the list. Okay. Now we're going to do that loop that we discussed. We're going to say while current is not equal, no, that wasn't it. Current next is not equal to null. Right? We want to stop at that last node. We want it to get to here. We don't want it to get to null. We want it to stop here when the next one's null. And by the way, this code is going to have a bug in it. And I know, so it's okay. If you're thinking, hang on. All right, and we want to just say current equals current arrow next. This is going to move current along until it gets to here. All right. Now, once we've done that, and actually even before we've done that, I could have made my variable new node, struct node, new node equals malloc size of struct node. And be very careful when you're doing the size of. Yes. When we'll have a break in. Do you want to have a break now?
As long as it's before 11:48. Any time is good. You can keep going.
I'll make this node, then so just when you're mallocing a node, make sure you malloc the size of the struct. Don't put a star in there. Otherwise, that's the difference between saying the size of, an address you've written down in your address book versus the house. It's not the same size. So be careful you put the size of the struct, not the size. Don't put this star in or anything like that. Don't do that. All right. So I'm making my new node. I'm putting the data in. In fact, I could have just called my function create node. That would have been easier. And I'm going to make it null. So my new node, imagine I'm putting 9 in there. I've got new node. Okay. And I haven't done error checking. I'm just leaving it for now, assuming my malloc worked. Okay. Now I want to connect it to the end, right? I want to connect current to this new node here. Just like I did in my much nicer diagram in the slide. So to do that, I said current, basically the next one after current should now be this new node. All right? So that's just exactly what we went through on the slide. Any questions? Yep.
Why are we not using pointer here? Current next equals to new.
Oh, because this is just the variable. So here, new node is a pointer, and that contains an address. If I put a star here, I'm trying to go to that address and get information out. If I just put new node like that, I'm copying the address in. Okay. Okay. I think we've got to go for a break. When we get, no, I'll just quickly run it. So let's compile this. Linked list insertion, linked list insertion. I haven't caught it. Let's go to a break. When we come back, I'll actually change the main function to use this function. We'll test it, we'll see what's wrong with it, and we'll fix it. Because there's something wrong with the stream, and apparently we've got to go for a break now. Okay, that's why. So let's come back at what time, guys? We don't know.
12.
Let's make it 12. We come back at 12. All right. I know I'm leaving you hanging right now. You're desperate to find out how this function works.